Hey, welcome to 5-8. Congratulations on finishing 5-7, relative frequency. We're into another probability study, and this is probability without counting. Sometimes this is called the area model for probability, and the way it works is we have an area, and we can look down at example 1. You see the 24-inch by 24-inch square, and in it is a 6-inch diameter circle. If we feel that it's equally likely that something could land anywhere within the 24-inch by 24-inch square, then the thing of interest is, well, what's the probability that it would land within the circle? It leads us to something like relative frequency. What's the total amount we have here? Well, it's the area of the square. What's the thing we'd like it to, the result we're looking for? Well, we're looking at to land within the area of the circle. And so this is our area probability. The key to it is that it's equally likely to land on any point within it. If instead we have a marks person aiming at this, and they have very good aim, well, that's not random at this point. Then the equally likely aspect of it tends to go away. So we want a situation where it's equally likely, it could be anywhere in there. Then how do we figure out this probability? If we look down at it, we know that the total area is the area of the square. That's 24 by 24, which is 576 square inches. That's our total area. Well, what's the area of a circle? Well, it's pi times the diameter, the radius squared. And so pi r squared, the diameter is 6 inches, the radius is 3 inches. So that's pi times 3 squared, or 9 pi. So an exact answer in this case would be 9 pi, or we could probably reduce that fraction a little bit, and that would give us an exact value. An approximate value would be one where we take 9 times pi, not 9 times 3.14, but hit the pi button on your calculator. So 9 times pi divided by 576, and that's going to give us about 0.049, or about a 5% chance that the probability of the dart or object landing in the circle, given that it could land anywhere. And so here we have in the tan box our probability formula, the measurement of the region of the event, that was the circle, divided by the measure of the entire region. It could have landed anywhere within the 24 by 24 square. What's the probability it lands within the circle? If we look at another idea of probability without counting, and this is a probability from length, so that's again a geometric quantity, and we have this freeway exit problem. It's an accident could occur anywhere between exits A and E. It's equally likely, which means it's random throughout that. There's as much of a chance of it occurring between A and B as between B and C. And it asks in our question, what is the probability that when an accident occurs, it happens between exits C and D? Well, the distance from C to D is y miles. So that's our area of interest. We would like to know for that length, that length of interest is what are the accidents that could occur? Well, it's basically the mileage. AE, the total distance, is W plus X plus Y plus C. So it could occur anywhere within there. So that distance is going to go into the denominator. We're going to divide by it. The area we're interested in, or the length we're interested in, is between C and D. That's Y miles. So we take the total length and we divide that into Y. Or to go the other way, we take the length y and divide it by the total length. And this would give us the probability of, or the relative frequency of an accident occurring between, or the probability of it occurring between C and D. You can look at the actuals and compare them to see if there's a problem. If you assume that it's equally likely, then in looking at the actuals, you may find that it doesn't, in fact, come up that way. So that's probabilities from length. You'll notice that we had no numbers in this problem. It was simply just looking at the variables that represented the distances and doing our calculation with that. If we had one with numbers, it probably would be a little bit easier, but the basic idea would be the same. Now let's look at it's a spinner activity. If you've got a spinner, great. They're easy enough to make. Get a 3x5 card, draw a circle on it, punch a hole in the center of the circle, get a paper clip, bend it to go through the hole, and then bend it back so it kind of stays put. Then holding the 3x5 card between your thumb and index finger, hold it up, and then you can flick the paper clip and have it spin, and you could mark your white and red area, or however you wanted to make your spinner. There's a 50% probability the spinner lands in the red region. It means 50% it could land in white. If we wanted to do this as an activity, we could simply spin this and see how many times do we get red and white. The probability of red and white should be 50-50. That's the probability, because basically of that total circle, half of the area is white and half of the area is red. It's just an area model. So 50% of the total area divided by the total area is going to be 50%. When we do this, we should find it. Now the relative frequency would be you're actually spinning it, and who knows what you get. You could try it a lot of different ways and see what you get. It may not always be the same. Okay, example 3. We're going to go through this one. There's a target consisting of 3 evenly spaced concentric circles. We're looking at this and saying if it's equally likely that we will hit the target somewhere within the circle, in other words, this region enclosed by the larger circle, that includes the blue, red, and white region. So if it's equally likely, what is the probability that it lands within the red region? Well, that's going to be the area of the red region divided by the area of the largest circle, the total area. Well, the area of the red region is simply this donut shape here. We have the white region is within what we might call the red circle. So we have to take this red diameter, which is 2 inches plus 2 inches, which is 4 inches, or red radius, excuse me, that's 4 inches, and we're going to multiply pi times 4 squared. That's the area of the circle with the 4-inch radius. And we need to subtract from it the area of the white circle, and that white circle has a 2-inch radius, so that's pi times 2 squared, which is 4, so we have 16 pi minus 4 pi. That leaves us with 12 pi inches squared. We're going to use pi in the calculation until we get to the very end of it, because as we'll see, it's going to cancel out. So our area of interest, the red region, is 12 pi inches squared. We want to divide that by the area of the largest circle. The area of the largest circle is determined by the calculation of pi times its radius, which is 6, squared. So pi times 6 squared is 36 pi inches squared. So we can show that the probability is the area of the red region, 12 times pi, divided by the area of the blue region, 36 times pi. The pi's cancel. Pi over pi is 1. 12 over 36 reduces to 1/3. Our answer is 1/3. If you had converted pi to a decimal, you were going to have a messy answer. It would not have been an accurate one. It would have been an approximation. So please carry something like pi through to the end. See whether it cancels. See whether it might be part of getting an exact answer. I hope this was helpful to you. If you'd like some more help, I'd be happy to go through some more examples with you in class. Come and see me. We can do this during class time. Your assignment is covering the ideas, applying the math. Good luck on the mastery quiz.